Been a long time since we've seen you guys. Been a long time since we've thought about physics. Been a long time since we've done problems involving multiple forces. We've done a number of different kinds of problems involving multiple forces, including elevator problems, and inclined plane problems, and pulley problems, and sometimes combinations of those. I want to do a few of those today just as examples, just to get our minds kind of back into the groove of physics here. So let's start off with an elevator problem. Let's say we got a guy standing in an elevator. Let's make it a girl standing in an elevator, because it's always a guy. Okay, it's a girl standing in an elevator. Her mass is 50 kilograms. She is moving downwards, but as she moved downwards, she is slowing down at a rate. She slows down at 2.5 meters per second squared. I want to know two things. I want to know her actual weight, and I want to know her apparent weight, how heavy she really is, and how heavy she feels. Well, we do the same thing for the elevator problem as we do for the inclined plane problem, as we do for the pulley problem. We draw a free body diagram because there's more than one force acting on this girl in the elevator. So we got a force of gravity acting down, of course, and we have a normal force acting up. Can anybody tell me how big I should make that normal force? Smaller or bigger than the force of gravity acting down? Yep. Why bigger? Good. If she's moving downward but slowing down, then the upward force must be bigger than the downward force. So normal force is going to be larger, got to be longer. Good. Let's solve for question A right away. This is an easy question, number A, or letter A. What's the actual weight of the person? M times G. Right? Weight is defined as the force of gravity, so all we're going to do is say it's M times G, which is 50 times 9.81, which is 490.5 newtons. Or we're going to round that to two digits. If we go back to here and here, two digits, 4.9 times 10 to the 2 newtons. Okay, that's the easy part of the question. Next part of the question, we've done this before, so none of it should be that hard. But this is definitely the harder part of the question. Let's say F net is equal to the sum of the forces, Fg plus Fn. F net is also equal to M times A, right? F net is equal to this, but F net is also equal to this. So therefore, MA must be equal to Fg plus Fn as well. All of those forces acting, all of those forces that don't balance out, that are acting on the object. The mass of this girl is 50 kilograms. For acceleration is, oh, wait a sec, we know that. What's its value? 2.5 or negative 2.5? Who says positive 2.5? Okay, a few of you. Who says negative 2.5? Nobody? Oh, a couple people? Okay. People that said positive 2.5, how come? Why is it positive? The upward direction? Why do you say negative? Because she's going downward, or because she's decelerating? Okay. Decelerating makes it seem like a negative value. Upward, normal force makes it seem like positive. Which is it? Here's the thing. It is a deceleration, but it's a deceleration in the negative direction. So you're right, Nathan, it requires an upward force to do that, a net upward force to do that. And if it's a net upward force, by Newton's second law, the force and the acceleration have to be in the same direction. So it's an upward acceleration as well. Even though she's moving downward, it's an upward acceleration. That makes sense? So we're going to make it positive here, 2.5 meters per second squared. Fg, we already figured that out. It's 490.5, but we're going to make it negative here because it's acting downwards. We're going to solve for Fm. 50 times 2.5 is going to give me 125. And we'll take the 490.5 over to the other side by adding. 615.5 newtons. All right, that's the normal force. What was I looking for? I wasn't asked to find the normal force. I was asked to find the apparent weight. So what do I have to do with this, Julia, to find the apparent weight? What do I have to do with the number I just found to give me the apparent weight? No? Bit of a trick question. It is the apparent weight, right? The normal force is the apparent weight. I could have said, what's the apparent weight? I could have said, what's the normal force? I could have said, what's the force of the floor pushing up? I could have said, if this girl is standing on a set of bathroom scales, what's the reading on the bathroom scales? The exact same question any way you look at it, okay? We're going to round this to 2 digits, 6.2 times 10 to the 2 newtons. And that's it. Got it? Well, if we're good with that, then we're probably going to be good with this. We'll give it a whirl, though, just in case. Let's put 3 objects here. Let's make this one 10 kilograms. Let's make this one 5 kilograms. And let's make this one, what do you say we make it 15 kilograms? Let's put a coefficient of friction in there of 0.20. What are the units that go along with the coefficient of friction? You guys remember? There are no units. Good. Another trick question. Now, this one looks a little bit more challenging than the last question because of the way that it's shaped, kind of the way that it's set up here. Okay, in the end here, you had 2 forces, one acts up, one acts down. Here you have 3 forces. It's only one more force. But it's a little bit confusing because one of them's right here, one of them's right here, and then you get this force of friction as well. We don't even know which way that acts. Here's what I like to do for these problems. We've done this before, so it's still just review, but straighten it out like this. If we straighten it out like this, it means we have this force that was acting downwards. Now we got it acting to the left. I'm going to call that F1, the force of gravity acting on number 1. We also have this force acting this way. I'll call that F3. Hey, why did I draw F3 bigger than F1? How did I know that it was bigger? I don't even know its value. How did I know that it was bigger? Yep. Good, because the mass is bigger, and obviously gravity acting on this guy isn't as big as gravity acting on this guy. Now, we do have friction as well. Can you tell me which way friction's going to act? Julia? Yeah, and how do you know it's going to act to the left? Yeah, so in other words, it moves to the right as a result of this force. And the direction of the friction is going to be opposite to the way that it moves. So I'm going to draw friction in right here. When I was going over a question similar to this with somebody during scheduled help, I think I drew friction like over here. Does it matter? Does it matter where I draw it? I mean, truly, it's acting on the 5 kilogram object, right? But I don't need to draw it on the 5 kilogram object. Okay, it's acting on the whole. It affects the system. So wherever you want to draw it, it doesn't really matter. Okay, let's get some of these forces here. Let's get the value of. Oh wait, there's a force of gravity acting down on this guy too, isn't there? Right here. Right? Why didn't I bother putting that in? It's not that I forgot it. Why didn't I bother putting that one in, Luca? Yeah, because the normal force cancels it, right? Doesn't cancel though on the 10 because it's not sitting on a table, right? The 10 and the 15, but the 5 is sitting on the table. Gravity is canceled by the normal force. I got a lot of stuff going on here, so I'm just going to erase those. Okay, let's get F1. That's M times G, right? Jared, what M am I going to use here? The 10, the 5, or the 15 in order to get the force of gravity acting on number 1? Good. So it's going to be 10 times 9.81 which is 98.1 newtons. And similarly, on this one, it's going to be 15 times 9.81. I think that gives me 147 point. Give me a second here. 147.15 newtons. Are you sure? Okay, 147.15 newtons. Now, friction is going to be mu times the normal force, which is going to be 0.20 times, what mass do I use here? M times G, right, is the normal force here. But what mass am I going to use here, Tyler? Is it 10, 5, 15, or some kind of combination? 5, good. That gives me 9.81 newtons. Now, take a look back at this last one. Hey, F net is equal to the sum of the forces. Now it's the same question, right? Now it's just F net equal to the sum of the forces, except this time we got 3 of them. F1 plus FF plus F3. Jared Holinsky, what mass do I use here for F net? Good. So 30 times A is equal to negative 98.1 plus negative 9.81 plus positive 147.15 newtons. Yeah, I don't know what that works out to be, but now it's easy, right? Now it's just a little bit of addition and division. Let's try one more old type of question. And then we'll take a look at a couple of different types of questions that we haven't seen before. Kind of seen them before, but kind of not seen them before. Here's an object. We won't put a pulley on this. We'll just make it a 10-kilogram object, and let's add a coefficient of friction. Okay, let's make it tougher. Let's add a coefficient of kinetic friction of 0.10. Let's make our angle 30 degrees here. So we draw our free body diagram. We got the force of gravity acting down. We've got the normal force acting perpendicular, although that's not quite perpendicular. Something like this. And then we have this force F parallel that is really the combination of the normal force and the force of gravity. We can draw that where we have, but we could also draw F parallel right here. Now, there is friction here. Can you tell me which way friction is going to act? Yep, Nathan? Yeah, it's going to act up the hill here. And we know that because, look, F parallel is the only force pulling it down the hill, moves down the hill. Right? You let a block go on a hill, which way does it go? Down the hill. Friction opposes that. It has to act up the hill. So if we can get the value of FF and we can get the value of F parallel, we're set. Let's see what we can do. Let's say sine, this is 30 degrees, right? Has to be, same angle as this. Let's say sine 30 degrees is equal to opposite over hypotenuse. F parallel is equal to 10 times 9.81 times sine 30, which I think gives me 49.05. Okay, there you go. There's F parallel. Now we got to get FF. And it's mu times Fn. But we don't know what Fn is, right? This is one of those questions where Fn is not just the same as gravity, m times g. So how are we going to go about getting that? Yeah, let's say cosine 30 degrees is equal to adjacent over hypotenuse. That's going to be equal to 10 times 9.81 times cosine 30 degrees. 84.957 newtons. Okay, so let's now say friction is 0.10 times 84.957. Okay, now it's easy, right? Now it's easy. Kind of, at least. Now we're going to say again, F net is equal to the sum of the forces, F parallel plus F friction. Why did I drop the normal force and gravity there? Why did I not include it? They don't cancel each other out. Why did I not include those forces? Yeah, I did include those forces. That is F parallel. Good. Mass here is 10 times A. I'm going to say negative 49.05. Although, Nathan, you may define it the other way. Positive, that's fine. If you do, then when I make this one positive, 8.495 newtons, you'd make that negative, that's all. Now it comes to the really easy part, right? Add those up on the right side, divide it by 10. Done. 8.4? 8.495. So what do we get for A? That seems to be a pretty reasonable number, right? Negative, because, well, we know it's going down the hill. 4.1, and we know it's going to be less than 9.81, because when you're free falling, it's 9.81. You can't accelerate more than that, right? So 4.1 seems reasonable. Good? All right. I'm going to do another question here now that's a little bit different. Now that you're back into the groove of things, now that you've seen physics at some point in the last 9 days, we're going to do a question that's a little bit different here. Okay. All right, let's draw a picture of this. Have a closer look here. It says a 20-kilogram wagon is being pulled to the right with a force of 100 newtons at an angle of 30 degrees above the horizontal. So let's draw the ground here first. Here's ground level. Here's the wagon. And you're pulling that wagon up at an angle like this of 30 degrees, which, you know what, that makes some sense, right? Because when you're pulling a wagon, you're not on your hands and knees pulling the wagon parallel to the ground. Now, it moves parallel to the ground, but you know that when you're pulling the wagon, you're pulling it up at an angle. 30 degrees, maybe 40 degrees, you're pulling it up at an angle. Okay, in this case, we're saying it's at 30 degrees. We're saying the value of that force, we'll call it FA for the applied force, is 100 newtons. Maybe you want to call it F1. Maybe you want to call it FW for the force of the wagon. Okay, whatever. We also have a force of friction acting on the wagon. Which way is friction going to act? Okay, remember, it's being pulled up and to the right. It's moving to the right. When you pull the wagon up at that angle, it doesn't go up at that angle. It goes horizontal, parallel to the ground. Which way is friction going to act? Moves to the right, friction's going to act to the left, right? So let's draw friction in here. Maybe you want to draw it over here. That's okay. It doesn't really matter, but draw it to the left. Its value is 50 newtons. Now, there are two other forces acting. There's the force of gravity acting down. Whoops, I was going to call that normal force. Should be gravity acting down. And there's the normal force acting up, right? How big should the normal force be compared to this force of gravity? How big should the normal force be? No, it's not equal. Why not? You ever find yourself, you're swimming in a lake or a river, deep enough river so you cover your whole body. and you go to pick up a rock, or even you go to pick up another person, or you go to lift another person, and you find that that person or that rock seems lighter, right, because of the buoyant force acting up, right? So the force that you have to push up with on the person when you're underwater isn't as high as when you're above the water because something's helping you, right? Buoyant force is helping you. Something's helping the normal force here. What is it? Good. There's a y component of an applied force that combined with the normal force will equal the force of gravity. That y component is not a new force. It's part of the 100. But there is an upward force that is there that's part of it, that Fy. That upward force is helping this upward force so that this normal force upwards doesn't have to push as hard. It's like when you're lifting that rock underwater. The buoyant force is helping you. You don't have to push up as hard as you would if the buoyant force wasn't there. So that's the bad news. The normal force and gravity don't cancel this time. The good news is that the normal force and the y component of the applied force combined cancel with the force of gravity. Does that make sense? So what are we left with? We're left with friction. What else are we left with? The x component of Fa. Remember, the y component's gone. It combined with the normal force canceled out the force of gravity. So all we've got left is FF and the x component of Fa. Now we can figure out what this is, which we should because we don't like funny angles. Let's say cosine 30 degrees is equal to Fx, that's the adjacent side, over the hypotenuse. So now we're going to say, look, F net is equal to FF plus Fx. We're going to say 20 times A is equal to negative 50 plus positive 86.6. Um, 36.6 on the right side divided by 20 is positive 1.8 meters per second squared. 2 digits. Because if you go back here, this is 2, this is 3, this is 2, this is 3. The least precise piece of data is 2. The weakest piece of data is 2 digits. Final answer should be 2. Guys, you see what I've done there? There's a lot of lines there, a lot of arrows, and a lot of stuff crossed off. We draw a free-body diagram showing all the forces. Friction, normal force, gravity. We often don't draw those because they cancel out. They don't cancel out here. So we're going to draw them in. Good news is they do cancel combined with the y component of the applied force. They do cancel. So what are we left with? Friction, of course, and then the x component of the applied force. Y component's gone. Left with the x component here. And friction. That's it. So we set it up like that. Is that okay? Now, you didn't have to do it in this question. We'll do it a little bit later on. Okay, but we'll wait a few minutes to challenge you with this. What do you think you would have done if you had been given not the force of friction, 50 newtons, but rather a coefficient of friction there? What do you think you would have done? Have to find the force of friction, right? Which is mu times the normal force. How do you think you'd find the normal force? It's not m times g anymore, right? Nathan, number 2? Yeah. We'll deal with that. We'll do an example of that in a little bit here. Right now, I just want to have you work on a couple questions like this. What I'd like you to do right now is to take a look at the back side of the page of your worksheet book, or sorry, of your forces worksheet book that you got on March 31st, 2 weeks ago, and do questions 16 and 17, please. These 2 questions that you see up on the board. Okay, you don't need to copy those out if you have your worksheet booklet. If you don't, then you'll have to copy them up from the board there. See what you can do with those, and then we'll take a look at them in a few minutes, and then we'll show you exactly what to do when you have that coefficient of friction as opposed to the force, like you're given in this. All right, if you guys feel pretty good about both of these questions, let's modify one of them just a little bit here, okay? Let's take the first one, and second question, we added friction to the first one, right? Let's add friction to the first one again, but let's add it in the form not of a force of friction, but a coefficient of friction. Coefficient of kinetic friction of 0.10. What's the acceleration now? All right. I'm going to move that actually, so kind of in a bad place. Coefficient of kinetic friction was 0.10. Let's say we've got gravity acting down. We've got a y component to this force acting up, and we've got a normal force acting up. Agree? We know that these three green forces will cancel each other out. The two upward forces combined will cancel the downward force. Now, we also have a force of friction acting this way, and we have an x component of that 30 Newton force acting this way. The net force here is equal to the sum of the forces. The sum of the forces that haven't canceled. The green ones have all canceled out. F net is equal to FF plus Fx. Right? Remember, the green forces have canceled out. They're gone. Okay? The only forces that we have left are the blue forces here. Force of friction to the left, the x component of the applied force to the right. Now, the mass here is 10 kilograms. The acceleration is what we're looking for. FF, hey, we don't know what that is. Let's go down here and let's figure out what FF is. Shouldn't be that hard. It's mu times Fn. It's 0.10 times the normal force. What's the normal force? 10 times 9.81, right? No. No, it's not. The normal force, look, the normal force plus the y component, the two upward forces, equal the force of gravity, the downward force. Does that make sense? Usually, for us, the normal force equals gravity, but the normal force is being helped by the y component of that 30 Newton force here. So it's the normal force and the y component combined that cancel gravity here. More bad news, though. We don't know what the y component is. How are we going to find that? How are we going to find the y component of that force? Well, it's the opposite side of the triangle. Sine 30 degrees is equal to opposite over the hypotenuse, which is 30. 30 times sine 30 is 15 newtons. So the normal force plus 15 newtons equals the force of gravity acting down, which is 98.1. Now, we do a little bit of math there, and we see that Fn ends up being equal to, what is that going to be? 83.1. That makes sense, guys? That's kind of a tricky step there, right? Upward forces equal downward forces. We just wanted to find out what Fn is. So it's force of friction is 0.1 times 83.1, which is 8.31 newtons. All right. Negative 8.31 newtons is our force of friction. Oh my goodness, we still don't know what Fx is. Well, that's not so bad. It's the adjacent side. So let's say cosine 30 degrees is equal to the x component over 30. 30 cos 30 is 25.98 newtons. So let's add 25.98 newtons there, the x component. Look, at this point, it's the same as every other question. F net is equal to the sum of the forces, FF plus Fx. It was just a little bit more challenging to get Fx and a little bit more challenging to get FF in this case. Now it's easy. Now it's easy. Negative 8.31 plus 25.98 going to give me somewhere around 18-ish, divided by 10, somewhere around 1.8. 1.8. So 1.76, we'll round it to 2 digits because of our data there. Thank you, Tasia. 1.8 meters per second squared. I'll tell you what, guys. That's about the hardest question on this material that you'd see on a test. Okay, it's possible to see that, but I can tell you again that you won't see anything harder than that, at least on this topic on a test. Okay, man, I'd love to throw in something like this, right? But 30 degrees. Hey, look at this. We're pulling it at 20 degrees above that. Don't worry about that. I'd love to do it, but it just wouldn't be fair. So okay, be ready for that, but don't worry about that. Good? Good? Let's try one last problem today, okay? One last problem that we'll do as a group, that is. And we'll have you do 1 or 2 practice questions on this. Just have a look at it. Write it down, and then we'll take a look at it as a group here. So here we got this, I don't know, let's say it's blocks of candy. It's a traffic circle? Well, can't pull on a traffic circle though, right? Let's pull it anyway. Okay, all right. All right. So we're pulling on a traffic circle, or a can of candy. Whichever you want to think of it, okay? However you want to think of it. Can of candy or a box of candy or a traffic circle. You're pulling on it in 3 different directions. 20 newtons straight up, 20 newtons to the right, and then 20 newtons down and to the left, and then go 30 degrees. That would be south of west, right? 30 degrees south of west. We want to know in this case what the net force is acting on this. Now, in all the problems before, up until now, where we've tried to find the net force or the acceleration, then we just said F net is equal to the sum of the forces, and then solved it that way. The problem is, in this case, I got a 2-dimensional problem. And if you look back here, look, I got forces going everywhere here. But if you notice, everything in green canceled. The only thing we're left with is everything in blue, which is all on one axis. Here, they don't cancel. Here, I'm going to end up with forces on 2 axes, x and y. So here's how we're going to deal with that. We're going to first of all say, when we see this, I don't like funny angles. So we're going to get rid of that. We're going to go off to the side over here, get rid of that funny angle. Here we got 30 degrees. It's a 20 Newton force. This is x, this is y. Let's get the value for x and y. Cosine 30 degrees is equal to x over 20. X is equal to 17.33. Sine 30 degrees is equal to y over 20. Y is equal to 10 newtons. Let's do this. Let's pretend that's not there. We got a force to the left. It's 17.33 newtons. And we got a force that's down. It's 10 newtons. Make sense? If this was a problem where I said, Nathan walks 20 newtons to the north, then 20 newtons to the east, and then meters, I should say, then 17.3 meters to the west, and 10 meters down to the south, you would solve that problem, no issues at all. We did those in the first unit. You guys nailed them. So let's treat it that way. Let's go x's and y's. Let's say 0 newtons for this one, 20 newtons in the y component, 20 newtons for the x component there, 0 newtons for the y component. Negative 17.33 newtons, negative 10 newtons. That make sense? Add them up. What's this going to be? 2.67 newtons. This one's going to be 10 newtons. Now what? Now what? You guys know the answer to this, right? We've never done one like this, but you know the answer. Last thing I'm going to ask you today. Now what? You got it. Right angle triangle. Vector diagram. 2.67 newtons this way. 10 newtons this way. The net force is the sum of those forces. But we can't just say Fx plus Fy. We've got to do the Pythagorean theorem to find the sum of those forces. So let's say F is the square root of 2.67 squared plus 10 squared. And then theta is the inverse tan of opposite over adjacent. Good? Okay, this half of the room here, Tyler's side of the room here, you guys are going to find F and MJ's side of the room are going to find theta there. Somebody on Drew's side of the room, what'd you get for force? Drew, you got it? 12.6 newtons. We're going to round that to 13 newtons because it's 2 digits. And somebody on OK's side of the room here? What do we got? Kelly got it? No? We got it? Granky, got it? So we're going to say 75 degrees, and that would be, according to this, it would be 75 degrees north of east, right? Because it's from the east measured above the east, north above the east. So for the first time in a lot of days now, we're solving a problem that's actually a little bit different. Right? It's not just, okay, here's a little bit more. This one's different. But the good news is, it's not really any different than what we did back in Unit 1. It's just different than what we've done over the last couple of weeks, that's all. Right? I'm going to give you a couple problems to work on here. We'll start off with one, and then if you do well on it, we'll give you another one to work on to finish off class here. Let's see, Terry's traffic circle is being pulled this way. We'll call that F1. The force of 100 newtons. Your question is, find the net force. Find the net force. Hey, by the way, if you wanted to find the acceleration, once you get the net force, what would you do? Just divide it by mass, right? You just don't have the mass here, so we're going to stop it there, ask you to find the net force, and then say, if you did have to find the acceleration, just divide it by the mass. Okay, see what you can do on that, please.